Today we're going to talk about functions and modeling. And so we're going to start with this question, what is a function? So a function is really a simple idea. The idea is you put something in and then you get something out. So whatever sort of situation you're in, if you can explain it in terms of putting something in and get something out, you can relate it to the function concept. Let's take a look at an example I have here of some functions, and there are really four ways to represent a function. You can look at it in terms of a table, and so when you look at it in terms of a table, you have the input here on the left and the output on the right. You can also look at it in terms of a graph, and so for graphs the inputs are along the horizontal, where the outputs are then along the vertical. And then the most abstract way of thinking about a function is thinking about it in terms of a formula. So here's the formula: 240x minus 2x squared. The last way is thinking about a function in terms of words. And so here we have the statement: you have 320 feet of fence to enclose a rectangular region along the side of a barn. Express the area as a function of one of its sides. So these are four different ways of representing a function. There's sort of four different mediums to work in. They all represent the same thing. So if you look at this, you'll see if you plug in 0, you get out 0. If you plug in 0, you get out 0. If you plug in 120, you get out 0. You may not know this, but this is actually inputs 120, and you get out 0. And if you were able to label the axis here, you'd see if you plugged in 60, right here in the middle, you'd actually get out a height of 7,200. So this table and graph are connected along with this formula. So the formula we like to write as f of x. This is functional notation, which we'll talk about in a little bit. And we can write this as f of x equals 240x minus 2x squared. You'll notice if we plug in 0, f of 0 is equal to 240, and wherever you see an x you put a 0, so times 0 minus 2 times 0 squared, which will give you 0. And you'll find if you plug in 120, and you can do this on your calculator, but you would take 240 times 120 minus 2 times 120 squared, and the number you're going to get out is also going to be 0. And you can check this on your calculator if you like. So if you have your calculator, you can practice this. Take 240 times 120 minus 2 times 120 squared, and yes, you get back 0. And the reason for this is that this table, graph, and formula all represent the same function, but in different ways. This is represented in terms of a table, this is represented in terms of graph, and this is in terms of represented formula, and what they represent is this word problem right here. You have 320 feet of fence to enclose a rectangular region along the side of a barn, and you want to express the area as a function of one of its sides. So you could express it as a table, as a graph, or a formula. We'll actually solve this problem at the end when we talk about modeling. So moving on here, we talked about the four different ways to represent a function in terms of tables, graphs, formulas, and words. We also want to talk about the domain versus the range of a function. And so the idea behind the domain, so if you're giving me a function, you usually have some inputs. And so the domain is just equal to the set of all inputs. Whereas the range is equal to the set of all outputs. So basically the domain is what you can put in to your function, where the range is what you get out of your function. So let's take a look at an example of this. So below here, what do we have? We have find the domain and range of the function. So the function is given to us in terms of a graph, and to find the domain we want to look at the inputs. Like I said before, the inputs are along the horizontal, and if you look over here at the input of 0, so here's 0 right here, there's nothing above or below it, so it's not in my domain. Not until I get to the number 1 right here do you see there's a graph above it. So my domain's going to start at 1. I'm going to put a closed parenthesis there. And then I'm good, because you can see above it there's a graph, and I'm good all the way until I get to 5. Now above 5 I have an open circle, which means does not include the point. So I don't want to include it, so I'm going to put a right parenthesis there. So for my domain, what I have, I'm going to write this in interval notation. So I have from 1, and I'll write closed bracket, because I'm going to include 1, and I'm going to go all the way to 5. And I'll put a parenthesis to the right of 5 because I don't want to include 5. So this is what's called interval notation. And it's shorthand for a set. So this is equal to the set. So we use curly brackets for a set. The set of all x such that the number 1 is less than or equal to, because it's closed bracket, we include 1, it's less than or equal to x, is less than 5. And it's less than because we don't want to include 5, because if you look at 5, you'll see that there's no graph above it. You have an open circle. Remember, it's easy to know that this symbol means less than, because if you rotate it a bit, it looks like an L, which stands for less than. And if you know that one is less than, then it's easy to know that this one is greater than, because it's the opposite. Okay, for the range, what we're going to do is we're going to start at the very bottom. So the very bottom starts right here, and it doesn't include the point. So we'll start here at the very bottom, some nice number between 0 and 2. So let's say 1. And then as you go up, you'll see you have a graph to the right. So here's a graph, here's a graph. You can keep going up. You continue having a graph to the right until you get to the very top point up here. Some number, nice number between 6 and 8. So let's say it's 7. And we'll include it because it looks like to the right it hits the height of 7. So for our range, these are our outputs. We'll say it goes from 1, left parenthesis, because we don't want to include 1, all the way up to the number 7. And we'll use a closed bracket there because we want to include 7. So if we write this in set notation, so again, this is interval notation, whereas to the right here, this is what we would call set notation, which we'll try to avoid for now. We'll try to use mostly interval notation. This would be the set of all x such that 1 is less than x and is less than or equal to 7. And I made a little mistake here. Since this is output stuff, instead of x, we should write what? Instead of x, we should write y. And so let's correct that. So this is all y, because it's output stuff, y, such that 1 is less than y is less than or equal to 7. Right, so there's my range, and there's my domain. So it's a very simple idea, although the notation makes it look rather complicated. And the idea is just what can you put into your function? That's your domain stuff. And then what do you get out of your function? And that's your range stuff. Let's go and look at this in terms of a formula. So here's a formula here, and we're not going to find the range for this formula because it's rather complicated. To find the range, we'd probably have to graph this, and it still may be rather difficult to see. But the domain for a formula is not too difficult because there are just a couple things you have to watch out for. So when you're working with a formula, you should remember for the domain, for right now, there's two things we need to concern ourselves with. The first thing is that if you have a function, you can't divide by 0. So I write this to remind myself, 1 divided by cannot be 0 in the bottom. And then the second thing you have to remember, if you're taking a square root, or actually any even root, you have to make sure whatever's inside here is bigger than or equal to 0. If it's not bigger than or equal to 0, then you're going to have to work with complex numbers, like suppose you had the square root of -1. And we don't want to work with complex numbers, we want to stick with real numbers. So these are two things I have to worry about. So when I look at g of x, I first ask the question, am I dividing by something? Right, so I'm going to look at this first one. Am I dividing by something? I say, yeah, I'm dividing by something. I'm dividing by x plus 5. So I need to make sure that x plus 5 is not equal to 0, because I can't divide by 0, which means that if I subtract 5 from both sides, x cannot be equal to -5. So that's the first thing I know. I have to make sure x is not equal to -5. The second thing I have to worry about is I ask myself the second question, do I have a square root? So you see that yes, I do have a square root here. So here's my square root. So I need to make sure the thing on the inside here, the thing underneath the radical, is bigger than or equal to 0. So I need to make sure x minus 2 is always bigger than or equal to 0. Otherwise, I'm going to get into trouble. I'll have to work with complex numbers, which I do not want to do. So I have to make sure x is bigger than or equal to, so I'll move over the 2, so I add 2 to both sides. So I have to make sure x is bigger than or equal to the number 2. Right, so now when I write down the domain, I like to do this intermediate step where I draw this on the number line. So on the number line, the way you can construct this is I know that x cannot be equal to negative 5. So over here, I have negative 5. So there's a hole there. And I know that x also has to be bigger than or equal to positive 2. So x is, here's 2, and it's bigger than or equal to, so it's all the stuff on this side. So what I have for my domain is anything that's shaded in. So this is shaded in, and I don't have that point, so it's actually just equal to 2, comma, to infinity. So maybe you can see this better if I kind of color code it. All right, so you see x is not equal to negative 5, so you have a circle here, and it could be all this stuff. That's what the bottom says. And then the top says that it has to be x is bigger than or equal to 2. And so that means that I have to be to the right of 2. And so with the red and green overlap, that gives me my domain. So D has to be from 2 to infinity, and you include 2. Alright, so that's how we do domain and domain with formulas. Let's talk a little bit about functional notation, because this is a bit of a stumbling point for students. So here's an example, and I just pulled back the graph and the formula we used before. And so for functional notation, we can do things like, here's f of x, it's just a graph. And I can talk about things like, what is f of 2? So the idea is the input is 2, so if input is 2, I go up here and I get this height right there, which is some nice number between 6 and 8, which I would say probably is 7. On the left, we have what's called functional notation. So that's functional notation. And on the right, we have basically the output. All the math stuff I always think is on the right. We can do this with a formula too. So you could do, let's do g of, let's say, 3. So on the left, this is functional notation. So g, when you plug in 3, what do you get? And on the right, you do the math stuff. So 3 minus 2, you take the square root of that, divided by 3 plus 5. So wherever you see an x, you put a 3. And so this is going to be equal to the square root of 1 divided by 8, which is just 1/8. So you have input, which is 3, output, which is 1/8. So that's functional notation when you have a function of one variable. You can also have a function of several variables. So just as an example, we could write down one. We could say f of x, comma, let's make another variable y, and we can create a formula. Let's say it's 2x plus, let's do 7y. And so we can write down in functional notation f of, let's say we plug in 5 and we plug in 1. This would be equal to, wherever you see an x, you're going to plug in a 5. So you have 2 times 5, plus wherever you see a y, you're going to plug in 1. So 7 times 1, which is equal to 10 plus 7, which is 17. So on the left-hand side, you have what's called functional notation. And on the right-hand side, you have the math stuff, which gives you the output of 17. What always helped me when I was first learning this was that I think of this as being a name right here. So g of x is just a name. F of 2 is a name. G of 3 is a name. F of 5, comma 1 is a name. And all the math stuff's actually on the right-hand side. Another good example of a function of several variables that we're going to take a look at in class is actually a car loan. So let me pull up this page here. So if you're going to get a car, you often want to know, how much your monthly payment is going to be. So here we have an auto amount, and so let's suppose we're going to buy a $14,000 car, and let's keep the auto term for 4 years at 48. So that's 48 months, and let's make the interest rate. Let's make it instead of 3.5. Let's make it 4%. The start date of the loan, it doesn't matter. We can start it to, this is 1/8/2015, and then we hit calculate. So those are our inputs, and if you hit calculate, it's going to calculate the amount of your monthly payment. So that'll be $316.11 a month. So what you see here are lots of inputs. That's what makes this a function of several variables. The variables include the amount of the loan, the length or duration of the loan, and the interest rate. And if you change these three numbers, you'll actually change this output right here. So suppose, instead of $14,000, you wanted to borrow $20,000, and you hit calculate, and it's going to give you $451.58 a month for your payment. And again, the idea of a function is you get input, and then you get an output. And that's the concept of a function in a nutshell. Okay, so let's go back to the lecture here. And so we've talked about these things. We've talked about the different ways to represent a function. So we can talk about them in terms of tables, graphs, formulas, and words. We talked about the notion of domain and range, the idea that domain is a set of inputs, the range is a set of outputs. We looked a little bit at functional notation, functions of one variable and functions of several variables. And we want to end this lecture with something on what's called modeling. And so modeling is a big part of where mathematics is used every day. If you take a look at what we just did here with the auto loan calculator, this is really a model. And it models how much you're going to have to pay each month if you take out a loan, in this case of $20,000 over 4 years at 4%. In class, we'll actually work with this formula so you can see what it actually is. And the reason why we don't normally work with formulas is because they're rather complicated to work with. It's easier to sort of program them into something or use a piece of technology and have a nice user interface that we can work with, and that gives us our answer. So let's take a look at a modeling problem we're going to do, which we kind of looked at the beginning of this lecture. So what we have is you have 320 feet of fence to enclose a rectangular region along the side of a barn. Express the area as a function of one of its sides. All right, so when we're doing a modeling problem, there's basically 4 steps you need to follow to help you solve this. And so the idea is you want to create a picture, come up with an equation, and then solve it and test it if the question asks for it. So in this one, we're just going to do the first 2 steps, but eventually we'll get to the last 2 where we solve, and sometimes we'll be able to test. So we'll create a picture out of the words. We'll come up with an equation, which is really sort of a plan of attack on how to solve it, and then we'll actually solve it later in the course. And if we can, we'll test our solution. So PEST, which stands for pest, and I always tell students it's sort of these pesty word problems so you can remember the steps. So what these steps give you is sort of a mental scaffolding that you can use to sort of solve any problem. So we'll start with the picture so I can sort of illustrate how this works. So P. And the idea is you have 320 feet of fence, so I'm going to write that down. So I have 320 feet of fence. And so we're working with area and perimeter stuff. So this is actually the perimeter. It's the amount of fence we have. And you can draw the picture here. You're going to make a rectangular region. And one side of this rectangle is going to be a barn. So I'm just going to put the barn on this side. It does not matter which side you put it on. So I'll put the barn, and let's draw it in red. So here's my red barn. And what that means is that this side right here does not need to be fenced because you're going to use the barn. And you want to express the area as a function of one of its sides. So let's label the sides. We'll label this side X, which means this side's X too. And then this side's different, so we'll label it Y. And so what we want to find, and let's say in this case, we're going to find a formula. So find the area as a function. And let's pick a side. So find the area as a function of, let's find a side X. and I always underline what I need to find, because the next step, my equation step, I know the formula or the equation I'm going to try to find. That's whatever you're trying to find right here. So find the area as a function of x. So I'm going to write A for area. So A is equal to, and I know how to find the area of a rectangular region. So the area of this region, the way you find it is you take length times width. So you take x times y. And so there's a formula for the area, but it's not my actual answer. The reason it's not the answer is because I want the area as a function of x. What I have is the area as a function of x and y. So somehow I need to get rid of y. I need to basically express it in terms of x. So then I have the area as a function of x. And the way we do this is you use the number you haven't used yet. So this is the perimeter of the fence. So I know 320, which is the perimeter of the fence. And the way you find the perimeter is you add up the lengths of all the sides. And now remember, I don't have to count the side with a barn on it because there's no fence there. So what I have is x plus y plus x. So I have two x's plus an additional y. And what I can do now is I can solve this for y. And so y is equal to 320 minus 2x. So I just move over the 2x. And then I can plug this in for y. So right here I have a y. And so I can simply plug in what y is equal to. They're the same thing. They look a bit different, but they're equivalent to each other. So then I can write a equal to x times 320 minus a 2x. And this is my answer. And so this is the area as a function of one of its sides, and as a function of this side right here. So you'll notice that this formula right here is actually the same formula that we had at the beginning, and you can even make it look exactly the same if you take 320 and you multiply through by the x. So x times 320 is 320x minus x times negative 2x is negative 2x squared. And so that's the same formula we actually had at the very beginning of this lecture right here. And the graph of this formula looks like this. And so what does that mean? That means if you have a length of 0 for your fence, then you have no area. If x is 60, you have 7,200 square feet for the area. If you let x be 120, then the area goes down to 0 again. You can even look at it in its table format. So if you have 20 feet here, you'll have 4,000 square feet for your fence. 40 feet for x, 6,400 square feet, and so on. So again, these are different ways of picturing this function.